Hello. We're going to try a problem that involves the basic properties of simple harmonic motion. A really good example problem uh, taken from one of the textbooks that involves essentially more than 5 goals that we're looking for, but these are nice and easy, and it helps us understand each one of the properties of simple harmonic motion. Okay? I've taken the liberty of writing all the given. I will explain it in a little bit. Goals and one of the formulas. I wanted to write some of them down as I talk to help explain what's going on. First things first, make sure you can underline, oops, that's not underlining, or encircle the given that you see, okay? And actually these are important as well, which reminds me that I actually forgot to put this. Okay, so we're given the mass in grams. Let's go ahead and convert that to kilograms, because we will be talking about newtons per meter in terms of the elastic constant, okay, of the spring. So that's not a really strong spring, but that's fine. And then we're given what's known as initial conditions, okay? These are important when we're trying to find the phase constant later on, and if we're doing any integration, but not necessarily in this case. And that's pretty much all that we're given, that at 11 centimeters, that's where the block is being stretched. If you look at the diagram over here, so this is it's being stretched that away to the right, 11 centimeters, and then let go. Okay, so you can already say off of the bat since we're not talking about damped harmonic motion, that the amplitude is, there you go, and you already have one of our answers even before I started talking about them. Okay, so that is our amplitude. And then up here, obviously, at this point, before it's released, it is at rest, or the velocity is at, initial velocity is at 0. Okay, let's go through all of these given. You already got one of them. Good to go. So the first one is properties on like the time properties of the simple harmonic motion. The angular frequency, symbolized by lowercase omega, which students often refer to as a W, the frequency itself, and the period. Now remember that frequency and period are actually reciprocals of each other. Okay, so that's how you get this formula here, that omega equals 2 pi f, or 2 pi over t. So if you find one, you're going to find the other. That's why they're all put in one goal. You already got the amplitude of the harmonic motion. The next is, what is the amplitude of the velocity function? And we'll talk about that right now, as a matter of fact. The formula for the velocity, the function is, if you look at the notes, is all of that, but we just need this part. Okay, so I'm going to actually erase all that, if you do not mind. If you do, I'm sorry, because we're just looking for the amplitude of the velocity, the maximum speed. That's what this is talking about. It's helpful to understand what it's talking about. And so if we look at the next one, the magnitude of the maximum acceleration, it's the same thing. So I would encourage you to look at the notes if you don't know what I'm doing. And boom, there you go. So you can see how this is dependent on that. Okay, I should just put an arrow right there. Okay, and this, since it's in velocity, is measured in units of meters per second, and this one meters per second squared. Okay, and there we go. Last one is we're looking for the phase constant. And that may be a bit tricky, but it doesn't have to be, as long as you know, oh, where am I at? There we go. As long as you know the initial conditions and your trig functions, you are good to go. Don't forget, unit circle always comes in handy. Okay, so that is the basic part of understanding the problem. Let's see if we can go ahead and solve this. We already have our amplitude, so let's go ahead and use our formulas to solve for omega. We are missing a formula. Okay, so you'll need that as well. And let's see if the units all pan out. So we're given, this pretty much takes everything that we were initially given, the mass and the elastic constant. Let's see if my units will come out what I'm expecting it to be. Okay. Okay, and it turns out that the calculated angular frequency is 9.8. What are the units? Well, let's check out the units. We have a square root of Newton. Okay, it's important to know how the units pan out. Remember that 1 Newton from Physics 1 is kilogram meters per second squared. Okay, so that's all of that from here. And take a look at that. The meters cancel out, and so do the kilograms. So what are we left behind with? We're left behind with 1 over seconds, whoops, squared. And then as you take the square root of that, that becomes 1 over second. But radians can pop out of nowhere, because radians is equal to 1 indeed. And how do I know I'm using radians? Because we're looking for angular frequency. Okay, so the units of this is radians per second. Now, since we're going to be using this value quite a bit, I recommend that you put this in the storage in your calculator, the storing function. So make sure you know how to use that. So once we have this, I'm going to use this equation, okay, to solve for frequency. Okay, so it's just that divided by 2 pi. Actually, I have 9.776 ... radians per second, because I'll round off for sig figs later on. Okay, and let's see what I get. Okay, I get 1.6. And by the way, this is the units of radians too, so the radians cancel out. I get 1 over second, or hertz. Okay, because 1 over second can be 1.6 cycles or vibrations or oscillations per second, or simply hertz. So, by the way, these are some of our answers right here. Okay, and for the period, and we're still on A, by the way, is just simply the reciprocal of that, or F equals 1 over T, but we're using the first one. So starting here, or actually I'm just going to erase that if you don't mind. And I'm keeping everything in the storage in my calculator so I don't have to round off. Actually 1.566 ... And it's 1 over second. Okay, so this second actually comes up on top, and that's exactly what we need because we're looking for a measure of time. and that is 0.64 seconds. A little more than half a second. Okay, and that is our A. So remember, we already have the amplitude. What was that? 0.11 meters rather, which we need to solve for the amplitudes. And I'm going to go ahead and, if you do this all together, and since we're talking about the amplitude, this has to be a positive value, because even though the oscillations go from positive to negative depending on what the equilibrium or the reference point is, we're just talking about essentially a scalar value. Okay? So let me plug in these values. We had 9.8 radians per second. Doing a little bit of shortcut there. But remember that the meters goes away. And because we are looking for something in the units, meters per second, so that is actually just simply 1. Okay, so 9.8 radians per second. Well, this one is squared. And why is that one squared? Because the units we want is meters per second squared. Okay, because this is just a 1 right there. Okay, let me pause for calculation. Okay, and what I got was, since it's 0.11 times 9.8, which is pretty darn close to 10, it practically just moved 1 decimal place. Whoops. Erase all that. Meters per second, and this one became 11, so the acceleration, the maximum acceleration is pretty big. Okay. So this is 1.1 for the velocity and 11 meters per second squared. And we're almost done. Okay, last part. The phase constant. Now for the phase constant, I guess I did forget one formula. You need the basic formula for simple harmonic motion that describes essentially the position of simple harmonic motion at any point in time. Okay, but remember, what is our goal here? We're looking for this guy, which you can't see yellow. Looking for that. So this is where initial conditions come to play. Okay, at t equals 0 seconds, x at 0, wait, hold on, I need more space, x at 0 equals the amplitude, okay, which is actually 0.11 meters. So I can have 0.11 equals 0.11 meters, which actually won't matter because we're going to cancel out anyway. And this is going to be omega times 0 seconds plus phi, which we're trying to look for. Okay? So hopefully you can see that that immediately goes to 0, so you're only left with this. And I can divide both sides by the amplitude. I don't even need to put the numerical value. Boom. And that doesn't go to 0 on the left side, by the way. That goes to 1. Whoops. It's a really big one. And there you go. So this kind of simplified quite nicely. Now you can use your knowledge of the unit circle to see what angle would give me, what if I take the cosine of that would give me 1, or just simply, if you want to do that straightforward approach, take the inverse cosine of 1, and from here you'll see that phi is indeed, if you make sure your calculator is in radians mode, it's a really good point, and sure enough, phi is going to be 0 radians. So my handwriting is not good today. Okay, ran out of room. They're just able to fit it in 2 pages. Okay, so take a look at all of that. I tried to speed things up in order to explain the different properties. Some were pretty obvious right off the bat, but you're using the formulas, including this one, to solve for different properties of simple harmonic motion, and make sure that you take a look at the units, because they should all converge and make sense to what you're trying to measure, whether it's angular frequency, time, period, velocity, acceleration, or even phase constant, which actually is an angle. Okay? Enjoy.